Hello and welcome everyone. In this presentation, we will be discussing our project work for the G30 Design Practice 2 class at Nagoya University. The content of the presentation are as follows.
So by using a ruler to measure all the data in class, the dimensions of the wooden flat plane, the stick base, as well as the balls and the basket can be measured and obtained, as can be seen in the two figures. And from the data in the two figures, we can construct a SolidWorks environment components in order to be simulated later.
From the dimensions that were measured in class, a simulation of the table with real measurements were simulated in SolidWorks.
The images on the right show the initial design which was printed. A rotating base was added to allow for small rotations. The slope was curved using a spline to stop a sudden force acting on the ball when it reaches the plane. Many other features were added as well. However, this design had a few flaws upon testing. They are discussed in the alternative design in the next slide. This slide shows the alternative design based on improvements made to the initial design. The initial design could not be rotated because of its square-shaped end. The new design has a circular end to allow for rotations. The ball had to be pushed in the initial design. Here, the flat section was made much shorter so that the ball rolls automatically. The rotating base was made thinner for stability. A cut was made for a manual gate, and other features were added as well. However, upon comparison, the final design was deemed more successful, so it was used instead.
In this alternative design, it was inspired by a tank design. But due to the inaccurate results as well as the design, which was a bit too complex for 3D printing, it was not used. From all the designs, a final design was made. It is considered to be better than other designs due to its accuracy. In order to make the design more complex, a rack and pinion gate mechanism was included, so we can only have to rotate the pinion to release the ball. After testing the pitch, we found the final pitch of the gear, which was shown in the right table. As you can see in the design, this is the final design with enhancement added to it. It is placed on the further edge of the table where the ball will be released. This slide shows the details of each of the enhancement pieces. We can see the handle, which is made from a pinion, and we can see a gate that was attached to a rack, and then we can see the design. These three components will be put together.
As can be seen, 3 different types of gates were tested in the experiment. Firstly, the long tube works by pulling it to the side to release the ball. Then the flat gate is one which can be either lifted upwards or moved sideways to release the ball. The gear gate consists of a gear which can be rotated in order to manually lift the gate to release the ball.
This slide shows how the camera will be set up in SolidWorks so that we can see the simulation.
To obtain the best SolidWorks simulation for the ball launchers, many properties should be concerned. These slides only show the most important properties, such as the properties of the ball as well as the Nagoya gravitational accelerations. For the ball, we only need to consider the materials, which is IBF plastic, the diameter, which is about approximately 40 millimeters, and also the mass about 2.7 grams. Other data, we can ignore it or set it by default. For the gravitational accelerations, these vary differently in many areas. In Nagoya, we choose G to be 9.79 meters per second square, as can be seen in the table. Next, we move to the simulation method. So for the launcher RAM, basically it has three dimensions, which are the length, the width, and also the height. We cannot design the launcher RAM when varying all the three dimensions. So finally, we decide to fix the length and the width, and we only vary the height to find the best optimal value. The length is fixed at 8.7 centimeters because it slightly doubles the diameter of the ball. So the ball will have enough or correct energy, both potentials and kinetic energy, to go to the right spot, which is also can be called the special point in the flat plate. And when the ball enters this point, it can correctly go into the basket. Secondly, we choose the width D to be 4.1 centimeters because it is slightly larger than the diameter of the ball. So the ball will not be shifted much during the throw of the launcher. After many trials and errors, the high edge is chosen to be 0.6 centimeters, which give the best optimal performance, as can be seen on this table as well as the figure here. So after a successful simulations on SolidWorks, we can export the data of the trace part of the ball to the Excel for further analyzing. So as can be seen on this graph, the ball reaches to the target goal of the basket as in real life when the horizontal data x is equal to 100 centimeters. Moreover, we can also approximate the trajectory of the balls in the perpendicular view to the best fit line of 6 polynomial order curve, as can be seen here. In other words, this is the equation of the ball in the wooden flat plate when reviewing in the perpendicular view.
This is the result of simulation from SolidWorks. In here, we use the final launcher and the table that was made to scale. A full video simulation can be seen in the video on the right.
Of image processing as well as programming, my task is tracking the trajectory of the ball in video. In my setup, I use Python as a programming language because Python has good interface with a lot of open libraries with state-of-the-art technology. In particular, I mainly use OpenCV for image processing in this task. In particular, my program works as follows. In the first frame of video, the initial ball position is selected by user. After that, the CSRT tracking algorithm of OpenCV will automatically track the ball trajectory throughout the video. That trajectory, represented in x, y coordinate, can be output in a CSV file to compare with simulation result later on. This method succeeds and it has consistent results.
This slide shows the results of the competition, which was held on the 26th of December 2020. It was quite remarkable that the ball went into the basket in the second try itself. In 10 minutes, we managed to put the ball into the basket 8 times. Then we decided to test out the different gates and bases to evaluate their performance. Overall, our design was quite successful.
In the next step, we apply the image processing for a success in the competition. You can see the detail in this video. We then repeat the image processing for many videos and notice that there are 4 typical trajectories the ball took as shown in the figure. We actually can attribute this error factor when launching to the dimension of the launcher. For example, as you see, the width of the launcher is slightly larger than the diameter of the ball. As a result, the ball can be shifted left or right, even a small extent when being launched. That can significantly affect the trajectory of the ball in our complex plan. Next, assuming we can overcome those factors and obtain a success in real life, we want to compare that trajectory to our simulation. As you can see, we already plot the trajectory in real life and the trajectory in SolidWorks in this figure. They resemble each other closely. Then we can confidently say that our simulation environment mirrors real life pretty well.
On those, we tried our best to create the best simulations of the ball launchers so that it can match the real life performance by measuring all the dimensions as well as considering all other properties such as the ball properties and gravitational accelerations as can be seen in previous slides. There are still some minor errors happen in the real test day. The reason for the error happening is because the ruler we use to measure all the dimensions has only one significant figure, which will affect not very significantly but still to some extent to the trajectory of the ball. Secondly, there are many assumptions have been made during the simulation, such as the static frictions, as well as the flat table stiffness, damping, and also the ball penetrations. So as can be seen in the figure here, the penetrations is set to be 0 millimeters with the assumption that the ball will not deform when rolling on the flat plane. So this is just one typical example to show that we made many assumptions during the simulations, but it will not affect too much on the final result as can be seen from previous slide. So the simulation curve and the real life curve nearly match each other very well.
This is the end of our presentation. Thank you very much for listening.